So welcome everyone to lecture 4 in this class from Transformers to GPT. Um, so outline for lecture today, we'll look at um, a little bit about training and back propagation, some of the fundamentals of machine learning in some sense. We'll continue to look at overfitting and hyperparameter tuning, and we'll also look at some other deep learning architectures. Um, and this will kind of round up our background on deep learning. And there's so much more in deep learning that we'll not be covering. But we'll kind of like finish here. And then we'll new to a new and exciting topic on embeddings and semantic search. So embeddings is such a useful concept that can help with making search smarter. There is traditional search like search engine search, and then there is semantic search that is like capturing the semantics of a query to then retrieve documents and then surface them. So that's kind of the essence of semantic search. So we'll kind of go into that as well. So some housekeeping items, right? Uh, Office hours and reviewers, these are set and you can find them on the web page. Um, Let me just see, where is it? Yeah, so you'll find it on the teaching support. All the office hours are listed here. So assignment 2 will actually be a mini project and it'll be assigned today. So it's going to be more hands-on. Uh, and it's going to span about 2.5 weeks. So we're going to actually be giving you about 2.5 weeks, and it's going to come in parts. So I think there is something about this. Let me see if I can. It might be better. So mini project 1 will have a part 1. We'll have a part 2. We'll also have a Kaggle contest, right? And through all of this, you'll get exposed to semantic search, embeddings. You'll also get to work with Streamlit, like kind of like demoing what you are learning. And you're also going to work on a Kaggle contest, right? So how many of us have participated in a Kaggle contest in the past? Show of hands. Okay. If not, this will be a first, and you'll see it's pretty exciting to be like work in teams and have a friendly competition with other team members, and in the process learn a lot. So the contest itself will drive you and motivate you to keep learning. So these are the elements that are coming up with the mini project. So it's going to be um, pretty. Okay. So yeah, it's going to be, I'm going to say it's going to be a little bit intense, more intense than an assignment. Okay. But you'll have 2.5 weeks, and there's going to be different things. You'll be coding, you'll be working with a demo, you'll be working with a Kaggle contest, and you'll be working with APIs, you'll be working with libraries. So it's going to be a lot of exposure, um, but you'll have help, and you'll have review hours, office hours, and we'll also go through some demo notebook today if we get the chance. So you get a feel for how it could be. Um, and to maximize learning, right? So we want to make sure that your learning is maximized based on past experience and how people have worked on this in the last year. We suggest that you form teams of two, right? So even if you have like your favorite 3, 4 people that you like to talk to, maybe split it into teams of two, and that way you can just break it down and then work on it, right? Only in the rarest cases, like the teams of two are already formed and you're left with 3 people, then you can have a 3 people team. But otherwise, like we'll be looking to see that you guys form a 2-person team, right? And I think the TAs will share a spreadsheet on the Discord channel where you can just put your name against, like you can put in your name if you want to form a team, and then you can give it a team name or something, and then someone can join you as well. So you can kind of have a way of like, if you already know people you want to work with, you can like pair up and put those names. Or if you're looking for people to pair up with, you can also again add your name to that spreadsheet. Does it sound good? Any questions on this? Okay.
Yeah.
Um, have you guys been able to use the office hours review session and the resources that we have? Any thoughts on that? Okay, cool.
Good, yeah.
All right, so let's move on. Um, so from last time, we kind of looked at perceptron and logistic regression. We looked at how a two-layer neural network can learn an XOR. And I think there was an in-class exercise that we probably didn't get to finish. Maybe we'll quickly round it up today in 10 minutes. And then we also looked at concepts of right fit, overfitting, and underfitting, right? This is a super important concept. You might work on LLMs and have absolutely no idea about what overfitting or underfitting is because you've not worked with traditional AI models. But it's important to know them for various reasons, right? I mean, not everything can be solved with an LLM, and there'll always be like regular AI models, machine learning models that you have to work with. And if you didn't know these concepts, you would not be in the best place. So we covered that, and we also looked at a TensorFlow demo that where we looked at how underfitting or a right fit or overfitting can happen. We looked at a few examples there. So today, we'll kind of like finish this exercise because it's good to like get hands-on with some of these activation functions and how the basic idea with doing this exercise is, uh, if you think about it, it's about how does the information flow, right? And from inputs to output. So what is this? There's a term for this on information flow from inputs to outputs in machine learning parlance. What would that term be?
What was
Sorry?
like a forward propagation?
Forward propagation. That's right. Forward propagation. Because we also have backward propagation backprop. We'll cover that in a bit. So going from inputs to output, the information flow is called forward propagation. And then when you flow the information back from outputs to input, and that's usually an error correction or optimizing the loss function, that's called backward or back propagation, right? Backprop. So this is important to understand, you might use deep learning models as a black box and not understand how the forward propagation happens. So we'll just quickly close on the example that was like an in-class exercise for you guys last time, but I think people didn't get to finish it. So we'll kind of actually do a walk through that, and then you guys can share as we build that table what the intermediate values are, right? So let me add a new page here. Okay, so we're going to I'm going to replicate this network and kind of make it a little bit more obvious. Um, so here's the inputs: 1, x1, x2, and then we have um, 1, v1, v2, and then we have y. Okay, and then we have let me add different colored arrows here so it makes more sense. So this is the information flowing into V1, right? So these purple arrows are information going to V1, and we have weights here. I'll just change the weights a little bit. So let me make it minus 0.2 or something. Yeah. And then this is 1 and minus 1. And then for the information flowing into V2, I'll use a different color. Um, yeah. So So this would be, let's say again, negative 0.2, and let's say it's negative 1, and then 1. Okay. And then we also have the information flowing into y. So let's say, okay, so again, I'm going to use something else like negative 0.3, 1, and 1. Okay, so assume this is the case. So now we're going to build a table, and we also said we want to, do we remember what activation function we were using in the in-class exercise in the intermediate layers?
It was a step function, right?
For the intermediate, I think it was ReLU, and
It was ReLU.
the last one was step function.
Yeah, so ReLU looks like this. Actually, we don't have a ReLU here. It's just here. And then the last one was a step function. Okay, right? So what we're going to do is we're going to delineate all the operations that happen from input to output through a table. Okay, so let me see if I can move this down. Zoom out a bit so it's you can see the whole table. Okay, let's build out the table. So say this is the table, right? So this will obviously be x1, x2. And then so let me call it v tilde 1, and then v1, and then v tilde 2, and then v2. And then I'll call it y tilde and y. So why is this? Why are we doing this? Because this is where we apply the step from the ReLU, right? And this is where we apply the ReLU. And this is where we apply the, what do you apply here?
Step function in the
We apply the
last
step
one.
function. Yeah. So let's, and we looked at 4 different inputs. So let's look at 0, 0, 1, 0, 0, 1, 1, 1. So maybe we'll see. I mean, in interest of time, we might do the first two, but we'll see if we have time, we can do everything else. So let's also write down the equations for V1 and V tilde 1 and V tilde 2. Yeah. So then it's more easy. So I'm going to write that down here. So V tilde 1 equals minus 0.2 plus x1 minus x2. Yeah. It's just taking whatever's on the purple lines and then expanding it out here. And V tilde 2 is minus 0.2 minus x1 plus x2. Yeah, because we have a negative here, right? And then I'm also going to write down what y is here. Sorry, y tilde is. Y tilde is negative 0.3 plus v1 plus v2. Okay, so these are the intermediaries. All the tildes are intermediaries before the activation got applied, right? And v1, v2 are with activation and y is with activation. Yeah. Okay, so what is v tilde 1? Let's start calling it out.
0.2.
Negative 0.2, right? So what is
Oh,
v2?
okay, yeah, yeah.
Yeah. So what is v1?
Oh, 1.
0.
0. Because the
Oh,
step
yeah, yeah, yeah.
function,
Yeah, yeah, yeah.
right? The step function takes anything negative and makes it 0. What is v tilde 2?
It's
Again,
also
look at this.
negative.
Minus 0.2.
Minus
Yeah.
0.2. Yeah. And v2?
0.
0
0.
again. Look at this. Look at this arrow. The purple arrow tells you what's happening with V2 given V1. V tilde 2, right? So what is Y tilde?
Negative
Zero.
0.7.
Yes.
Negative. So, sorry.
Points.
Or, I mean, if it's, you can also put in the chat. Might be faster if you put in the chat as well. So what is Y tilde? Look at this equation here.
Minus 0.3.
Minus 0.3. Now, what is Y given Y tilde? So this is the step function applied to Y tilde to get Y.
Zero.
0. Okay. Okay. So these are the transformations that happen from x1, x2 to get to Y. Okay, let's look at 1, 0. What is V tilde 1? So again, going back here.
8.
0.8.
0.8.
Yeah.
So what is V1?
0.8.
0.8. You know why? Because this ReLU function, if you look at this part, this portion, right? What is this portion? This is this is equal to x if x is greater than 0. So it
It's
just
just a linear
replicates it.
pass.
It just lets it pass. If it's less than 0, it just truncates it to 0.
It's kind of like a diode.
Yeah. So it's a it lets it go forward. Okay. So now what's V tilde 2?
-1.2.
Negative 1.2, right? So what is V2?
Zero.
0. So what is Y tilde?
Minus 0.5.
Minus 0.5. Anyone else?
7.
So you have to take in V1 and V2 here, and
Oh,
then subtract negative 0.3.
0.5. Sorry.
0.5. So what is Y?
1.
Y is 1. So unlike ReLU just lets it pass it as is, right? But what does step function do? It says you're either 1 or you're 0. Pick one, right? So now that you're on the positive side, you get bumped up to 1. Whereas ReLU will say, I'll keep you at 0.5. Does it make sense? So
Yeah.
again, you have to look at what step function we're using here versus here versus here. Okay. So looks like we're in the right direction. Yeah. And let's look at, I think, yeah, let's look at 0, 1 just to complete it. What is V tilde 1? It's negative something. Negative 1.2. Yeah, you guys agree? And V1? V1 is
0.
0. V tilde 2?
Mm. 0.8.
0.8. Yeah. You have to plug in 1 here and 0 here, and you have negative 0.2. So that's 0.8. So what is V2?
0.8.
0.8. What is Y tilde? Remember, you use V1 and V2. So Y tilde uses the activated neurons, right? V tilde 1 is not activated, but V1 is activated. Similarly, V tilde 2 is not activated, V2 is activated. Y uses the activated neurons to inform its value, right? So what is Y tilde?
0.5.
0.5.
0.5. And so what is Y?
1.
1.
Okay, let's complete it. Actually, let's just complete it so that we have a complete table. So what is V tilde 1 here?
1.8.
So look at this equation here. And you plug in
Negative
Right, right,
0.2.
right.
negative 0.2 because in this case, I mean, I'm just, kind of expanding on it. It's negative 0.2 plus 1 minus 1.
Plus 1 minus 1.
Okay. So that's negative 0.2. So V1 is,
0.
yeah, V tilde 2
Negative 0.2.
is negative 0.2 minus 1
Plus 1.
plus negative 1. Sorry, plus 1.
Plus 1.
Plus 1. This is again negative 0.2, right? And
Yeah.
so V2 is 0. And so Y tilde is,
Negative 0.3.
so you get exactly the same, right? It's kind of same values for both. And so you get Y is 0. So is this a good network for XOR? Did we get the right Ys? Is the Y correct if X1 and X2 are as such here? Yes. If X1 is 1, X2 is 0, you want Y to be 1, right? So that's correct.
Yeah.
If X1 is 0, X2 is 1, Y has to be 1.
1. Yeah.
X1, X2, yeah. So now the thing that we asked last time is what if we had instead of negative 0.5, we had negative 0.3 or something else, right? Yeah. So if you notice, you'll probably be right on the edge because if you have negative 0.5, you'd actually V tilde 1 would be negative 0.5. Okay, V1, V2, and Y tilde would be negative 0.5. Okay, so that's fine. What about this in this case? So V1 would be, if you have negative 0.5, V1 would be 0.5. So V tilde 1 would be 0.5. And V2 would be 0. That's fine. So Y tilde would be 0. You see, in the second case, if the coefficient or the intercept was negative 0.5, Y tilde would be 0. And so you're right on the edge. You could go this way or that way, right? So that's why we've changed this coefficient here to be something smaller in magnitude so that when you're positive on the Y, you're very confident. And when you're negative on the Y or 0 on the Y, you're also confident. If this was negative 0.5, you'd be right on the edge when you go from Y tilde to Y, right? In the previous case, Y tilde would have been 0 if X1 was 1 and X2 was 0. So you're not confident. So the confidence of the prediction is also important. And so these values did matter in that context. Okay. Is this table clear and how the forward flow, forward propagation is happening in this network? Yeah. So now imagine changing these with linear activation, sigmoid, other activation functions. You should be able to understand how things change. Yeah. So you should be, I mean, you should be able, so ideally you should be able to pick up a network and then pick it apart. Should be able to say, oh, this is what's happening. This is the activation function here. This is what's happening. This is the pooling. Okay, we're doing attention here. So you should be able to pick apart every single network and understand how the information is flowing on a high level, right? So this exercise helps with that. Okay. All right. So we kind of closed here on what we started last time. And this was one of the in-class exercise. So this was an IC from last lecture. So we kind of finished it up. Okay. So yeah, this was what we said. Okay. So we didn't get to 0.7, but imagine making this number even smaller, and then you'd probably get there. Okay. We looked at overfitting. I think we kind of covered overfitting. So let's move on. Some more motivation for deep learning is computer vision is one of the fields that actually took to deep learning and like saw a huge amount of impact, right? Previously in computer vision is the field of looking at images or videos and understanding or parsing it. And now it's also extended to generation, right? So you have image understanding, you also have image generation. So these are the kind of the broad areas, right? And within this, you will have other things like, you know, um, instance segmentation and image to text and all of that stuff. So image generation, you might have text to image or just random image generation, etc. So traditionally, computer vision has mostly focused on image understanding. Image generation was like way too advanced. So people didn't even look at it. I mean, there are like developments like GANs that started looking at image generation and image smoothing and image fine tuning, but image understanding was the most, like the focus was mostly on image understanding. And so in traditional computer vision, people were focused on handcrafted features. So you would kind of look at an image and then say, let's do a convolution, uh, let's do some pooling, let's do something else to extract certain features from an image. And then you would use a simple classifier like logistic regression, which we already looked at, or SVMs. And then you could answer a question like, is this a face? Is this a cat? Is this a dog? You know, things like that. Or is there a person in this image? Right? That could be a um, that could be a question. Is there some object in this image? So traditional computer vision has relied on extracting features through feature engineering, right? But that has changed a lot after the advent of deep learning. And feature engineering as such, if some of you have done it, it's actually time consuming. It takes a lot of domain expertise, and you have to spend quite a bit of time fine tuning the features so that when you actually apply the classifier afterwards, it'll do a good job. So deep learning changed all of that, right? So in deep learning, you just pass in the images or some uh, some feature, raw features extracted from the image, and then just pass it through the layers of deep learning model. And then you let the deep learning model extract fine-tuned features and do the feature engineering for you. So the idea with deep learning can extract fine-tuned features automatically, right? So it does it for you. So you don't have to worry about it. And then once the features are extracted, you can make the prediction, right? So here's an example of a deep learning architecture. In like early 1980s or even 1990s, it was just called neural networks because the differentiator with deep learning was there's more layers. So the layers are deep. So that's why it's called deep learning. But even deep learning is just a neural network, right? At the face of it. So traditional neural networks might have had only just one hidden layer to keep things simple, and there was computational issues. So computational issues, memory issues, and so you wanted to keep the network simple, right? But with the advent of like with the improvement in computation, storage, memory, infrastructure, GPUs, uh, scientists realized that they could just also work with deep learning neural networks. And so then they started adding more and more layers, right? Like for instance, if you have like an input image and the image is captured in terms of pixels, maybe even maybe it's also in grayscale, doesn't have to be color. Grayscale pixels of the image. Then a deep learning model would start to go from coarse grain features to fine grain features, right? So, sorry, coarse grained features to fine grained. So edges could be more coarse grained. Like, is there an edge in this image? Like if you have a table has an edge. If you have a wall has an edge. So understanding even if when we look at images, right? Like let's say someone blindfolded you, right? And then they took you to a room and they said, surprise, there's something here. as soon as you open your eyes, there's a little bit of orientation that happens, right? And you might be in shock because you're taking in the overall, oh, okay, so I'm outdoors right now. Okay, that's the first thing I understand. Oh, there's trees and then there's this thing. And then you start identifying the finer details of a image. Isn't that how we humans do it? And so that's the same idea with a neural network deep learning model is like you start with like overall scene understanding. Is there edges? Is this there? Is that there? Is it an outdoor image? Is it an indoor image? And then you start understanding like fine-grained features. Like for instance, if this is a face, as you go fine-grained, you might understand this, there is eye, there's a nose, and there's other things in the image as well. So, and then the fine-grained features are used to finally make the prediction about what this image is about. In this case, this image is perhaps an image of George Washington, right? So, but to get there, I need to go from coarse grain to fine grain, and that's how the deep neural network is able to tease out the features at different granularity and then use the fine grained features at the very end to make the prediction. Yeah. So, so with the advent of deep learning neural networks, feature engineering came for free. And so you just had to pass in a lot of data. That's the job. Previously, you had to not just give the data, but also do feature engineering. But now feature engineering has gone to the background. You just like, don't worry about it. The neural network takes care of it. It'll kind of figure out the features. Just give enough data, enough inputs and enough output pairs. And now the deep learning model will figure out how to construct the features and how to go from coarse grain to fine grain. So here's another example. I mean, in terms with notation as well, right? So the input layers, let's just say input is X, and then the cross connections between layers, we call it the weights, right? And it typically represented as a weight matrix. And this is a matrix because for any, from a given node, all these edges may form one row of a matrix. But then there are so many such neurons, right? And so you'd have multiple rows. And so those rows make up the weight matrix. So this whole crisscrossing that you see can be represented as a weight matrix, right? That looks like this. So every single row and column has a particular weight value. Uh, and then we also have hidden layers. And the hidden layers have an activation function, and typically activations you'll see in literature represented by A. So A shows that there's been an activation. Maybe it's a ReLU activation or something, right? It could be any one of those activation functions. And then the output layer comes at the very end, and that also has an activation function. Typically, if it's softmax or something, it'd be a sigmoid based activation function so that you get a probability here. So probability vector. Okay, so this is a neural network with 3 hidden layers, right? Okay. Right. So here's a question, and maybe you guys can take like a couple of minutes to think about this. Is an in-class exercise. Um, I know we haven't been grading in-class exercise so far, but maybe from the next lecture on, we might start grading your in-class exercise for some credit, so you can also actively participate, right? But right now, you can just maybe take 2 minutes to look at this question, and you might have to do some computations, right? Uh, is consider a deep neural network model with 3 hidden layers, right? Just like this. So one hidden layer, second and third, right? Um, and assume each hidden layer has 1,000 neurons, okay? And let the input layer be a raw pixels from 100 by 100 image, and the output layer has 10 dimensions. So if I have a 10 class image classification problem, so that means, uh, and that's the reason the output layer is 10 is because you want to classify the image into 10 different classes, right? If it was just like, is this a cat or a dog, you'd have 2 dimensions. So the number of output dimensions show the number of classes that we are making the prediction for. So the question is how many total parameters exist in the deep learning neural network model? So I would encourage you to actually take your pen and paper and take the next 2 minutes and kind of draw out how the structure looks like, right? So you have the input, you have the hidden layers, and then you have the output. So what are the dimensions here? And then what are the number of weights here, right? So the weights here 1, 2, 3. Did we capture everything? Yeah, and then 4. So there's actually 4 sets of weights, right? Because this is the input, this is the output, and then we have hidden layer 1, hidden layer 2, and hidden layer 3. Okay, so think of this structure right here, and then look at the question, map out the numbers to each of these layers, and figure out how many parameters are there in total for this deep neural network. So just take a couple of minutes and then work on this problem. Okay, so hopefully you got a chance to look at it.
I got a quick question.
Yeah. Yeah, go for it.
Yeah, sorry. How do we know if we need to consider the biases? I remember, I think last class you said something about biases, but I couldn't remember what it was. Of like, sometimes we don't consider them.
No, we do consider them. It's always good to have the biases. Just in case there is any bias in that's needed by the model, we always consider having the biases in the model.
I mean, like when we're counting the parameters, we would just add the number of neurons we have, basically.
Yeah,
In the
but the
hidden layers
biases would only add to the change because it's just one value per,
per neuron.
yeah, per neuron. Yeah. So
Okay.
it not
It won't
uh
make it 13 million, I understand, but I'm just asking the
yeah.
question for the sake of the question. Like, is there a reason, like when you read it, you interpret that there's no bias, or it's just because it's just an example?
No, I think, like even for a given neuron, uh, so we have like a bias value that's assigned to every layer, right? So like the one that we saw in the previous one, that's only adding like 1,000 per, from one for one, for two, for three, for four, right? So that's only adding to the change. It's not actually adding to the overall value. So the magnitude is still 12 million, but we would probably add to the change. So if you had an extra neuron here, or here, or here, right? These guys that connect to this bias would only add 1,000 uh, per layer. So that's why it adds to the change. Yeah.
And Professor,
Okay,
the
thank you.
bias for the output layer would be if we have 10 classes, then 10 neurons and then 10 bias.
So the output layer is just going to be 10, right? The bias will happen here. Like you might have an extra bias value in the hidden layer, right? So the output itself is going to be exactly the number of classes.
Okay, I was thinking about from layer 2 to the output layer, then would be 10.
So layer 2, you mean hidden layer or
Yes,
H2?
to the output layer.
No, but we're looking at from H3 to output, right?
Mhm.
So output is connected to H3, right? It's not connected to H2. So this is H1, this is H2, H3, and then an output.
Okay.
Here you have 10 classes. And this could be like your bias. And these are all the other activated neurons. Okay.
Okay.
So from here to here, the bias is adding like 10 extra parameters. That's it. Okay. Okay, let's look at the next one. It's a little bit about training, and this is going to be probably the only space we talk about training in a much detailed way, but we'll look at fine-tuning LLMs, we'll look at supervised fine-tuning and other kinds of fine-tuning. But here we are looking at like a fundamental question is, how do you even train a deep neural network? So the main algorithm or approach that's used to train a deep neural network is stochastic gradient descent with mini batch, right? This is kind of what happens under the hood. Gradient descent with a mini batch. So the idea is that if you have like lots of data points and each row is a data point, stochastic gradient descent will pick up on a few of these and call it a mini batch. And then it'll use this mini batch to inform the weights. And this is done through backpropagation, right? And then it'll go to the next mini batch and it'll do the same thing. And I'll go to the next mini batch and then do the same thing. And these mini batches are picked at random. So there's a way to randomize these mini batches. And you can have mini batches that are like in random order. So you can pick one from here, here, here. So you can pick it in any way. And you use the mini batch, and the typical mini batch size is like 128 or 256. So even if you had like a million data points, you would use a mini batch of size 256, and then you would run through all of the data points in some random order by covering these mini batches, right? And each mini batch will inform something to the weights. It'll change the weights in some way because there'll be the current set of weights, and then you do forward propagation, you get some error between the ground truth and the prediction, and then that for that mini batch, the error gets propagated back and it changes the weights. So that is what the procedure to do that is the stochastic gradient descent, right? So we're not going to go very much in detail on this. This is a whole different topic. We can go very deep into optimization algorithms, but um so yeah, so mini batch stochastic gradient descent is kind of like the engine behind machine learning in general. So any machine learning algorithm, modern machine learning algorithm these days has some version of stochastic gradient descent running in the background to do the training, right? If you're to train an AI model, including LLMs, even LLMs are no exceptions. As long as you have a neural network, you are using stochastic gradient descent behind the scenes. It just might take a long, long, long time to train an LLM, but what's training it behind the scenes is stochastic gradient descent. Yeah, does it make sense? So there are some things specific to stochastic gradient descent, like things like what is stochastic about it? Well, what is stochastic about it? What do you guys think?
I I believe it's called stochastic because it's like a single point in a random.
Yeah, so stochastic and stochastic gradient descent refers to the idea of randomizing the data. So the stochasticity is coming from randomizing the data, right? How do you pick a mini batch? I could pick the first 128. I could pick the last 128, or I could pick it at random. Like if I have like 100,000 data points, I could just like pick the first one, then pick the 100th one, pick the 50th one, pick the whatever, right? And then until I get to 128. So there's ways to randomize. That randomization is bringing the stochasticity in the model, right? But once you pick that data set, everything else is deterministic. So stochastic is randomness, and randomness is from the data. But once you pick the mini batch, it is deterministic. But overall, it is a stochastic algorithm. That is, it is random. So every time you run the training, you might get a different set of weights, right? Which, and then even the starting point could be random, right? Where the initial weights could also be random, and the way you pick the mini batch is random. So all of this adds to the stochasticity of the stochastic gradient descent, right? And that's why sometimes you train a model and you get a response, and you're like, well, I trained it once and I got these set of weights, but I trained it next time and I got a different set of weights. Why is that happening? Shouldn't I be getting the same set of weights on the same data? It's the exact same data, but I'm getting a different set of weights. And that's because of the stochasticity that's built into the optimizer behind these machine learning algorithms, right? Um, so, but also it was shown that stochasticity is necessary. If you have stochasticity, then the model performs better. The learning happens well. So in the word machine learning, learning refers to how you can learn the weights, how you can fine tune the weights. And that learning happens well if there is stochasticity and there is theory behind it on why, if you did it that way, you do better than if it is deterministic. So that's all goes into optimization theory and stochastic gradient descent theory, which people have published papers on. And this used to happen a lot in the early 2000s. There's a lot of papers coming out on stochastic gradient descent, and people actually publish papers on it. But now it's like bread and butter. Everyone knows about stochastic gradient descent, and they just assume that's like what you would do under the hood, right? And so you just let it, like you don't think about it so much. But if you pick apart a PyTorch library, or you go behind and see what's actually happening, you'll see that there's a stochastic gradient model with certain learning schedules and things like that. Okay, any questions on that? I think we'll um, take a break for 5 minutes after this, and then we'll come back. Okay, so we were discussing that stochastic gradient descent is like in short, it's called SGD. So SGD is like the main optimizer engine, or can even say training engine for almost any machine learning model. Okay. All right. So let's look a little bit about how the learning happens. So the learning happens um, through gradient propagation, right? So uh, gradient is like the mathematical quantity that transfers information for learning um, weights in a DNN, or deep neural network, right? So it's amazing. Like us, whenever you have a loss function on the parameters, then you say that the new parameters is like the old parameters minus some um learning rate times the gradient of the loss function at the old parameter. So this is kind of like a very vanilla, it's called vanilla gradient descent. Is when you do this repeatedly and you go from, um, you go from W0 to W1 to W2, WK, and then you say, okay, after K iterations, whatever weights I have, this is like the trained weights. And these are like the starter. The starter weights could be very bad, but when the training is happening, every time you go from let's say W1 to W2, this equation gets triggered, and the gradient of the loss function at that weight vector or weight matrix conveys the information on how to correct for the errors. So every time you have a new set of weights, there are some errors, like it's not perfect. So those errors get propagated backwards through gradient descent, and that's what is called backpropagation. So backpropagation is actually just a way to compute the gradient. Once you have the gradient, the learning happens. The learning happens by adjusting the weights. So all of training in deep neural networks is just weight adjustment or weight fine tuning based on this information flow from gradients, right? And it's not just any gradient, it's a gradient of a loss function. And a loss function is typically how well are you performing and what is the expected truth. You remember in that XOR function, we got a y at the very end. Suppose that y was incorrect, but we know what the correct truth is. We have a loss function that says how far are you from the truth. The farther you are, the higher the loss. That means more work needs to be done to improve the weights, right? So as we do gradient descent, what happens is that if this is the loss function, or let's say this is the loss value, and this is like the weights that keep getting changed, or this is like the iteration. typically as you iterate, the loss function kind of goes down and then flattens out, right? So and then your this might be your training loss and your test loss might look like that. This is test and then this is training. So you probably want to stop at a point where the test loss or the validation loss is starting to go up. So that's a place to say, okay, stop your training. I think we've kind of, and this is the point where you are not like, this is the point where you would, if you keep training, you would probably overfit. So you stop at a certain point. For modern deep learning models and even LLMs, you would probably do just one pass over the data. Sorry. So yeah, for LLM training and any big model training, the thumb rule is you do one or two pass over the data because the data itself is so huge. You might have millions of data points that you don't have time to go through the whole data multiple times. So you might just do one or two passes, and that's the thumb rule, right? And because you have so much data, this overfitting issue is not a problem, right? So the whole idea with gradient is that thing that helps you correct for the error of a loss function. And loss function, like some of the simple loss functions look like this, like w minus, I don't know, w hat. So there is like an ideal w, like the truth, and then there is the w that you have, right? But it could be even more complicated because you might actually want to uh, look at all data points. So like it could be like there's different kinds of loss functions, but um, like we typically use cross entropy, right, for classification. So you might do something like um, minus yi log y hat I is 1 minus yi log 1 minus y hat I, something like this. And then you average over all the data points. So I is like the data, right? So across all data points, so let's say there are n data points, you divide by n. So you say, what does this cross entropy look like? Because if y hat I is close to yi, then my loss will be 0. If not, the loss will be high. So you want the prediction y hat I. So this is the prediction. And then this is the truth. So for the ith data point, I know what the truth is. It's 1 or 0. Let's say for classification, binary classification, and then I have my prediction y hat I. That could be a probability between 0 and 1. It could be 0.8, 0.7, whatever. Across all the 1,000 data points or 100,000 data points, what's the average loss? So that is what L captures. It's the average loss across all these data points. And hopefully that is going down as we train, right? And that's how you know you're making progress. Okay. So, and if you notice, this is a function of W. Where is W here? The W is because y hat is a function of W, right? How you remember how we got the forward propagation in the XOR? We actually had to go through the weights to get to y. So that's why in this function, y hat is actually a function of W, the weights and the input. And that's how you get to the prediction. So once you have a loss function, you can construct a gradient. Once you have the gradient, the math is that if you go in the negative direction of the gradient, you typically decrease the loss. So that's how the information uh, is propagated. And then if you do a few iterations of it, you've trained the weights, and now the trained weights are ready to make predictions. Yeah. And the way to do the training is stochastic gradient descent. So you do compute the gradient, but you don't just apply to all of data. You actually have to do it in a mini batch fashion. So that's why it's called mini batch stochastic gradient descent. Because there is randomness, that's stochasticity. There is gradient for information flow, and there is mini batch because the information is taken only from a small batch of data points versus all data points at once. So this formula works for uh, learning pretty much uh, any AI model, any modern AI model, right, that we encounter would go through such a training. Okay, any questions so far on this? Okay, so let's look at forward prop versus backward prop. Forward prop, we already saw. If this is the inputs X and this is the outputs Y, forward propagation is what gets you from x to y, right? So basically compute outputs given inputs. That's forward propagation. Backward propagation is the flow of information from output to input, right? Is like flow of info or gradient computation from output to input. So the idea is like I do a forward propagation with certain set of weights and I get a y, okay? So let's say, let's call it y hat, right? So let's say the y hat is 0.3, but y is 1. Is y hat a good prediction in this case? No, because y can only be between 0 and 1, and you're actually going towards 0. So this is not good. So then you say I have to change the weights in some way. So I have to take the information from here and move it backwards so that the weights can change everywhere. And that is back propagation. So whenever you encounter errors between the prediction and the truth, you kind of pool it together, not just take one data point, but you pull it across a mini batch or 100 or 200 data points and say, let's collect all the errors. Let's pull it together and then pass it backwards through the layers so that all the weights get updated to reflect that there has been an error, right? And so now hopefully we'll do better. But again, you do a forward pass and you might get something like y hat is 0.6 and then y is 1. You say, okay, 0.6 is better, but it's still not great. Again, you do a back propagation. So you do this multiple times, but across a bunch of data points until you feel that the loss function is small. The loss function is small doesn't mean that you're making perfect predictions, but you're making better predictions than if you didn't train at all, right? So that's for sure. So backprop, I think there is some math behind it. We can go into as much detail as needed, but essentially it's like a way to compute the gradient, right? So this figure is actually reversed. The outputs are here and the inputs are here. So the back propagation is this way. Yeah. So in the previous figure, the inputs were here and outputs were here. So the back propagation was that way. But since you change the order of input and output, the back propagation is always from output to input. So we're going this way because of the way it is set up. So the idea is that if I want to compute uh, the information flow of the, based on the error, I have some error E or a loss function, and then I want to compute the, let's say, the how to update the weights here, right? So then I want to compute the partial derivative of the loss with respect to this neuron, dgj. I would use chain rule to say that, well, if you want to connect these two, maybe connect these two, and then use that to help you get the information for G. So that's basically what it's essentially applying chain rule. So the derivative of E with respect to Gj is the derivative of E with respect to H, the hidden layer here, times whatever residual you have, the derivative of that. So that's how you kind of like I don't want to go too much into the math of it, but essentially you can think of it as like, how do I compute the gradient across all these weights that are there in all the layers so that I can actually get the full gradient for all the weights and then update them, right? So every single weight, so every one of these should get the information from the output, right? And so to do that, I might have to use chain rule and then update the weights. So that's basically what back propagation is. So backpropagation is one of the fundamental backbones of training modules, right? Behind deep learning, including ChatGPT, LLM training, anything that's modern AI uses backpropagation. And it's just a way to unravel gradient computation in the neural network, right? So maybe in some other, like if, like for example, let me ask you this question, right? So suppose you have this function f of w is w square. What is the gradient of f? So gradient in this case is just the derivative. So what would you say the derivative is?
Yeah.
Sorry. 2W, right? Because this is basically df by dw. If you have seen df by dw, this might be familiar. Is you just take the derivative of w square, you get 2w. So suppose I have f of w1, w2. Now I have two weights. Then I say this is w1 squared plus w2 squared. What is the gradient of f? This is actually the partial of f with respect to w1 and partial of f with respect to w2, right? So what is this?
2W1,
And 2w2.
W2.
But this is equal to 2 w1 w2. So if I represent w as a vector, it is still 2w, but this is a vector, right? So this I can represent as w equals w1 w2. Okay. So gradient of f is actually in this case 2w, where w is a vector. All right. So gradient, essentially the dimension of the gradient is the number of parameters. So going back to this question, right? If I had this neural network, what would be the dimension of the gradient?
I'm gonna guess that it's the whole 12 million.
It's the 12 million. So every time there is a pass of information like 100 data points that you pass through a mini batch, those 100 data points are going to inform 12 million weights. Does it make sense? So, and that's how the gradient's dimension is the number of weights. So if it's 12 million, that's how big your gradient is going to be. And that's how much information that needs to get updated. So the information from 100 data points gets propagated to all these 12 million weights and they get updated. And then again, you go through the next set of 100 data points or 200 data points. And again, these 12 million weights get updated. So that you can see that's a huge computation. And that's why training can become, and this is just for 12 million. Imagine a LLM, right? LLM would be having who knows how many parameters, like billions or trillions of parameters. So a trillion quantities get updated with a single gradient update. Isn't that crazy? And then you have to do that so many times. And hopefully all of that converges and makes sense. Right? So, but that's the beauty of stochastic gradient descent. It says as long as you follow this rules of stochasticity and you do it in this way and you get the gradient, I'll do the job for you. We'll make sure that we start to converge to something meaningful. So, yeah, great. So if it's already a little bit complicated to compute the gradient of a two-dimensional function, imagine how complicated the gradient is for a neural network with billions of parameters. And that's where backpropagation comes and says, don't worry, we'll just go one layer at a time, and we'll do backpropagation as a chain rule to make sure every single weight's partial derivative gets computed. And then we can use it to update the gradient, and we can use it to update the weights, right? So all the weights will get updated. Okay. So if someone asks you after this class, what is backpropagation? What would you say? Um, I hope you would say that it's a way to compute gradient efficiently on a neural network, right? And then, and it uses chain rule, and then you can use it to propagate information and do the training, right? Okay, cool. There's some more things. Let's see, good and bad. Yeah, this is also important. Um, So if you notice with deep neural networks, it's not enough to just say, I have the data, I have the loss function, I have cross entropy, just train it. A lot of times people will say, do you want to set the learning rate? Do you want to set the, do you want to set any hyperparameters, like how many hidden layers are there in the network? Do you want to set anything else, right? So these things can decide if uh, your model is going to converge to a good local minima or a bad local minima. So there's theory around it, but you have to do, there's parameters of the model, which is like the weight matrix, and there's hyperparameters, which is like the kind of like the settings, you can say, the settings of the neural network that will ensure that you go towards a successful training. A successful training happens, right? So here's a quick question for you. Which of the following is not a hyperparameter in a deep neural network? Right? Just
Professor,
sorry.
I have one question. In the previous slide,
Uh-huh.
so are we looking to see for the global minima or the local minima?
Yeah. So for deep neural networks are highly non-convex functions. So there used to be a time when people will focus on global minima and say we want to get to the best global minima of a loss function. Like in this case, let's say this is a loss function. Like I want to maybe get here because that's like the global minima. But the theory now is that it's good to be okay with a nice local minima than aim for a global minima because you're optimizing for training data. For test data or evaluation data or real data, this might actually not be conducive in some sense. So, and also with stochastic gradient descent, you can never guarantee a global minima of any kind, but you can maybe do things to get to a good local minima. So this is still good, even though it's not the best in training, this might still be good. So a local minima that's generalizable, I think that's the word. So local minima that can generalize, which means that it's not just something that's good for training, but it's also good for testing and evaluation. That means something that doesn't overfit. So, right. So this is again another way to say it doesn't overfit. Okay.
Thank you.
Actually, I mean, I think although this is a question, let me just share that learning rate is definitely a hyperparameter, right? That you have to choose. That's kind of the most important thing. Like, and if you change it significant, like you can set it to 0.01, 0.1. I don't know if this might be part of your assignment one. You might already have looked into it. Um, is you might notice that if you change the learning rate, it might significantly impact the training, right? The training can become faster or slower. So typically higher learning rates, uh, higher learning rates is faster training and lower learning rates is slower training. However, there are disadvantages. Like sometimes if the learning rate, like you would say, okay, then just keep the learning rate really high. Actually, what happens is after a certain point, if the learning rate increases, the model weights will start to diverge. They will not converge. If they don't converge, then you're lost. So the learning rate has to be in an appropriate range that it's not too small that you're not learning anything, but it's not too high that there's a risk of divergence. So this is typically a sweet spot. And people say, hey, pick something like 0.01 that would work well. So, so you would probably get suggestions like that. So if you decide a neural network, sometimes the deep learning architecture, these things get fixed. So they're not treated as a hyperparameter in that sense. But if you would also pick the deep learning architecture, then these are also hyperparameters, right? But once you pick a deep learning structure, then learning rate is something that you definitely want to fix. Um, Also, type of nonlinear activation function. This is also something you might choose as a hyperparameter. Like, am I using tanh? Am I using ReLU? What am I using, right? So those are some things to think about. Um, and there's like ways to tune these hyperparameters. Like, how do I pick the learning rate? Well, you can actually run parallel experiments. You can say, let me set the learning rate to be 0.1. Let me set it to 0.01. Let me set it to 0.001. And then I'll actually train and see which one is giving me a better loss function. So that's a random search. And there could be, you can also do like other things like Bayesian optimization, adaptive search. But these are like a little bit of a detail. We don't have to worry about it too much. But essentially, you have to, for every single one of these, you'll have to train the model by fixing the learning rate or fixing the activation function and then see how the performance is. And then you go to the next set of hyperparameters and again you train. So that's like the settings. You figure out which setting is good for which the training happens well. That's the hyperparameter tuning process. Okay. Let's see. I think overfitting. Yeah, maybe we should cover it. Uh, Although overfitting is not something we worry about so much because it's taken care, we'll still look into some amount of overfitting. There are some specific strategies for deep learning models that can handle overfitting, right? Overfitting is when the number of data points is typically less than the number of parameters, right? We spoke about this. Like if you have, as a simple example, suppose you had something like this, then overfitting might be like, this is the curve that fits through these points, right? And maybe a good fit might be something like this, right? So it's not like really specializing to the data you have, that's overfitting. So for instance, like this used to be a problem before, it's not a problem anymore. It's not a problem so much for LLMs, is that a deep neural network model could have 100 million parameters. We already saw a model that has like 12 million parameters. Just imagine increasing the neurons and hidden layers, you'll easily get to 100 million parameters, right? So if a deep neural network model has 100 million parameters, but you only have 100 data points, 100K data points, you can see that 100 million data is, sorry, 100 million parameters is much greater than 100K data points. So there is a potential to overfit in this kind of a scenario. So this is where people use strategies like regularization. They make sure the weights don't go beyond a certain threshold, or so these regularization can be something that gets added to the loss function, and that can help with overfitting. And then the other common strategy is dropouts. So you randomly drop out certain weights in the certain neurons in your mini batch pass. So you don't update certain weights. You only update the other weights. That's called dropouts, and that works out to be a good strategy. And then there's one more as well, which is called early stopping, which is when you stop training the model when the validation error starts to increase, right? So if you have something like this, we spoke about this earlier, is let's say this is training error, loss function, and then this is a validation error. So if you notice at this point, the validation error starts to increase, right? So this is validation. So you just stop at this point and say, I'm going to stop here because I believe my validation is going up. I might be overfitting. So that's another way to, and these are strategies that are already implemented in PyTorch. You might see some of these are like already set in some of the libraries that do the training. Okay. Here's an example of dropout, right? If this is a standard neural network, you drop out certain weights, and then you only update these weights for a mini batch. And then in the next mini batch, you again drop out certain weights. So these are some strategies that were that are being used for training neural networks, right? And avoid overfitting. Okay. Yeah, we looked at tensor playground last time, so I'll skip this. There are more deep learning neural network architectures, right? So let's look at some of them here. We won't be able to cover everything, and but this is like there is an article or reference that calls it the neural network zoo, where it's a zoo of models that are used for different contexts. And so let's quickly take a look at this. So some of the important things I would highlight here are the input cell, um, the hidden cell, right? The hidden layers, the output cell, and also the convolutional. Okay, we also have recurrent. So convolution network, yeah. So this is convolutional cell, and then there's a recurrent cell, which is this one. Yeah. So if you look at the neural networks, there's so many different kinds of neural networks. We looked at perceptron, right? Perceptron was like a single neuron neural network. And then we said from perceptron, you can go to feed-forward neural network, which is like stacking up perceptrons. Then you have a deep version of it, which is the deep learning model, deep neural networks, right? And then there's also recurrence. Recurrence is when you have to generate the next token given the previous token. So this is the, if you remember, we said, we looked at the example where we said, um, I arrived in New York yesterday, or I arrived in, yeah, New York yesterday. The next city I would like to go to is blank. And that blank was, we said maybe Seattle or some other city, but not New York, right? So the next word prediction, the next word generation, recurrence is important. And even a GPT model is based on recurrence because you pass in the previous token and then you get the next token. So that's the idea of recurrence, is that the structure of the neural network stays the same, but you just replicate it again and again, but you pass in different tokens because the first token you passed in might be different from the next token you pass in, but the network has the same structure, right? So imagine it as frames, right? You have a frame, and then you have the next frame, and then you have the next frame, and then the next frame. These frames have the same set of weights, but the inputs coming in here are different. This is X1, this is X2, this is X3, this is X4. So the idea of recurrence is that these are all recurrent. They're all the same. They just keep coming again and again, but the input tokens keep changing, right? So then that's how you might say, if you look at how even a GPT is generating a sentence, right? It's like, I would like a cup. So again, you pass in I, you get would. You pass in, right? So you get would, and then you pass in would, you get like, and you pass in like, you get a, and so on. So that's the idea, is you keep passing in what you got out as the output from the previous recurrence, and then you keep moving forward. Quick question.
Yeah, so earlier you said that you worry less about features because the neural networks themselves are learning them. And so here you have displayed these sort of, chart different types of neural networks. And so I just sort of conclude that these different neural networks can learn different features. Is there then just kind of a kind of chart or meta characterization of what networks can learn what types of features or are good for learning what types of features and kind of group that together?
Yeah, that's a good one. I think we'll cover it maybe in the first 5 minutes of the next lecture. But I can quickly share here, but I think that's a good one. I think that would be a functional understanding of why we would need different architectures, right? So architectures, people do pick and choose even today. Like it's not like I would just use this architecture. Like even though it's like, everything is a neural network because they have neurons, but the neurons get structured in different ways and then they get called architectures. And so you may want to pick a certain template of arc or a certain templated architecture for a certain data type, also for certain problems, right? I'll just quickly mention, right? I mean, if you look at autoencoders, these are used quite a bit for a very popular generative AI application. Any thoughts on what?
Oh, what was your question?
So autoencoders are getting used for a specific generative AI application that that you might have already used in the last 2 years, but they're very popular.
ChatGPT.
Not ChatGPT, but if you go to the image space, image generation is based
Mid-journey
Midjourney, yes, but the underlying architecture behind it is
is
based
GAN.
is so actually it's based on just pull this one.
Is it?
So it's not, it's GANs are definitely used, but this, there is also autoencoders that get used in generating images as well. So if you look
Yeah.
and so these are called denoising autoencoders, and you can basically pass in noise and then generate
Yeah,
a
yeah, yeah.
Yeah. So,
Diffusion.
sorry?
Diffusion.
Yeah, stable.
Yeah. Stable.
So if you've heard of this word stable diffusion, they specifically use an autoencoder architecture. And the idea of autoencoder is it's auto. So the input that you pass in is the output you want to predict. In this case, it's images. So you want to pass in an image and generate an image. The catch is the information starts to get compressed more and more and more and more. And so you are looking at like in the middle of this architecture, you have like very few pieces of information or neurons. But from there, you can still generate an image with full clarity. So that was an amazing innovation with stable diffusion is this particular architecture and not any random deep learning model was able to enable image generation of high quality. And that surprised everyone that this was even possible, right? Question?
So I'll let you finish. I do have a follow-up question though.
Yeah.
You're done.
So stable diffusion depends on the autoencoder architecture because the idea, I think, and we'll cover this when we get to stable diffusion in more detail, but the idea is that you can add random noise, generate random noise, and then add in some text input, like I would like to see an image of a house, and then it will use the random noise with the combination of your text input and generate an image of a house. But the next time you try that, because of that random noise, you'll notice you cannot replicate the same image. How many of us have noticed this? This is an issue with Midjourney because that's how the network is. There's random noise sitting right in the middle, and then you add in your text input. But because that noise keeps changing every time, you get a different image. But if you had fixed it, if the noise was fixed, you would get the same image. So, but things keep changing. So autoencoders are a very good application example of an architecture that are particularly suited for image generation with like we see with stable diffusion. Okay, question?
Yeah. So I feel like the question I asked before was kind of assuming like we think we look at something like an image and we see features like you described in it, like you described before, like a background, foreground, all this stuff. But those are concepts we're using, and we think we're projecting that into something we think is there in these neurons. And so, but what about just like how do we, I mean, what tools do we use or how do we go about analyzing what features the network itself has learned? Not as we just necessarily might project onto it, but like maybe it's the network's not looking at the background first, or it's not doing things in the order in which we would necessarily do ourselves in classifying something and making a distinction of any kind, you know?
Yeah. Yeah, that's a good question. So this goes into the topic of interpretable uh, deep neural networks, right? So people like, the understanding LLMs is like really out of scope because of the humongous nature of the number of parameters and everything. But people, what they do is they pick even smaller models that still do reasonably well and then see how the intermediate layers look like. If it's an image, what's happening there? If it's text, what's happening there? And they interpret that this is kind of what's happening at a high level. And so there are studies done on that. I think when we get to interpretability for large language models, we'll probably cover that. Okay. But there is a method to the madness. So it's not just I mean, it is madness, that's true. Because you throw in a lot of wow, so my thing crashed, but that's okay. We're almost at time. So you throw in a lot of like uh, parameters at a data point, and then you hope that it actually does the job, right? So that's kind of the madness of it. But then there is a method to the madness, which comes in from interpretability studies, and so shows that deep neural networks have some method to it, to the madness that it follows, right? And then it's able to, you can interpret it to some extent, right? And the bigger the networks, the less the interpretability comes in. But definitely there is like studies that done on that. And including things like the initial layers are coarse grain and the later layers are fine grain. the initial layers are more high level understanding and the later layers are more deeper understanding. And that's how also transfer learning works is people like in, let's say you want to, let's say you trained let's say you train a model to understand images, and now I want to add on text, like I want to caption the image with a text, right? So then I have to have a text generation model, but I also have an image understanding model. And you can actually pair up an existing image understanding model with a text generation model by assuming that the earlier layers of an image understanding model understand and capture the features of an image. And the later layers you can just truncate because they are specific to image classification. But the earlier layers you keep as a way to transfer the learning from images to captioning. And then your caption generation model, which is a text generation model, gets appended to the image generation model. So that's how you can see that there is interpretability to the earlier and higher later layers at some level, right? But specifically what's happening on this neuron or that neuron, that might be hard to get information on, and it might be hard to analyze, right? But at a higher level, you can definitely see patterns emerging in these deep neural networks. Anything else we want to cover? I think it's a good place to stop because the next thing I wanted to cover today, that's probably a full lecture. We'll go into embeddings and semantic search, and we'll probably cover it tomorrow, 4 p.m. to 6 p.m. And it'll be a recorded talk. So I understand it's not a conventional time tomorrow because it's not on the schedule, but it's like we have to cover for the missed class last week, and we have to keep moving forward. So if you cannot make it, that's okay. But if you can make it, we'll have a Zoom link and you can join in tomorrow again at 4 p.m. And it's going to be a lot of material, and we'll also have a demo on semantic search. So you can see how the concepts start to tie in, right? Okay. Any questions before we finish today? Nelida, you had a question?
Yes, are you going to be with us for the tomorrow's lecture or the TA, or is you?
Oh, tomorrow's lecture, I'll be giving the lecture. Yeah.
Okay.
Yes. So I'll be there, and tomorrow actually there's a lot of material. So if you can make it, I would encourage you to make it. Is a lot of material, and it's amazing. It's very interesting, very exciting. Semantic search, and we'll also have a demo connected to it. So, and the demo is something you'll also work on in your mini project. So you'll actually see things in action. So I'll highly encourage you to make it tomorrow if you can. If not, you can see the recording.
When will the mini project be posted?
So we have Rahul here.